In polynomial functions, I will be looking at functions of x that represent polynomials of varying degrees, including cubics and quadratics and quartics. We will look at some of the properties of these curves, and then we will go on to look at how to deduce the function of the curve if given the roots. So first of all, what is a polynomial? Well, a polynomial of degree n is a function of the form f of x equals an x to the power n plus an minus 1 x to the power n minus 1 plus, and it keeps going all the way until we get to a2x squared plus a1x plus a0. And here, the a's represent real numbers and are often called the coefficients. Now, this may seem complicated at first sight, but it's not, and hopefully a few examples should convince you of this. So, for example, let's suppose we had f of x equals 4x cubed minus 3x squared plus 2. Now, this is a function and a polynomial of degree 3, since the highest power of x is 3, and it's often called a cubic. Let's suppose we had f of x equals x to the power 7 minus 4x to the power 5 plus 1. This is a polynomial of degree 7, since the highest power of x is a 7. An important thing to notice here is that you don't need every single power of x all the way up to 7. The important thing is that the highest power of x is a 7, and that's why it's a polynomial of degree 7. And the final example, f of x equals 4x squared minus 2x minus 4. It's a polynomial of degree 2 because the highest power of x is a 2. And it's often called a quadratic. Now, it's important when we're thinking about polynomials that we only have positive powers of x, and we don't have any other kind of functions, for example, square roots or division by x. So, for example, if we had f of x equals 4x cubed plus the square root of x minus 1, this is not a polynomial because we have the square root of x here, and we need all the powers of x to be positive integers to have our function to be a polynomial. Second example, if we had f of x equals 5x to the power 4 minus 2x squared plus 3 divided by x, once again, this is not a polynomial. And this is because, as I said before, we need all the powers of x to be positive integers. And so this 3 divided by x does not fit in with that. So this is not a polynomial. OK, we've already met some basic polynomials, and you'll recognise these. For example, f of x equals 2 is a constant function, and this is actually a type of polynomial. And likewise, f of x equals 2x plus 1, which is a linear function, is also a type of polynomial. And we could sketch those. So we've got f of x and x. And we know that f of x equals 2 is a horizontal line, which passes through 2 on the f of x axis. And f of x equal to 2x plus 1 is a straight line with gradient 2, which passes through 1 on the f of x axis. So this is f of x equals 2, and this is f of x equals 2x plus 1. Now, an important thing to remember is that all constant functions are horizontal straight lines, and all linear functions are straight lines which are not horizontal. So let's have a look now at some quadratic functions. If we had f of x equals x squared. We know this is a quadratic function because it's a polynomial of degree 2. And we can sketch this. It's a very familiar curve. If we have f of x on the vertical axis and x on our horizontal axis, we know that the graph f of x equals x squared looks something like this. So this is f of x equals x squared. So what happens as we vary the coefficient of x squared? And that's the number that multiplies by x squared. So if we had, for example, f of x equals 2x squared, how would that affect our graph? Well, what actually happens is you can see that all of our x squared values, i.e. the f of x values, have now been multiplied by 2 and are hence stretched in the f of x direction by 2. So you can see we actually get a curve that looks something like this. And this is f of x equals 2x squared. And likewise, we could do that for any coefficient. So if we had f of x equals 5x squared, it would be stretched 5 times from the value it was when it was x squared, and it would look something like this. So this would be f of x equals 5x squared. So this is all for positive coefficients of x squared, but what would happen if the coefficients were negative? Well, let's have a look. Let's start off with f of x equals minus x squared. Now, compared with f of x equals x squared, we've taken all of our positive values and we've multiplied them all by -1. So this actually results in a reflection in the x-axis, because every single value is now, which was positive, has become negative. So f of x equals minus x squared will look something like this. So this is f of x equals minus x squared. Likewise, f of x equals minus 2x squared will be a reflection in the x-axis of f of x equals 2x squared. And so we get something which looks like this. This is f of x equals 2x squared, sorry, minus 2x squared. And lastly, we're going to look at f of x equals minus 5x squared. And you may well have guessed by now, that's a reflection of f of x equals 5x squared in the x-axis, which gives us a graph which would look something like this, where f of x equals minus 5x squared. And in fact, it's true to say that for any polynomial, if you multiply the function by -1, you will always get the reflection in the x-axis. Now we'll have a look at some other quadratics and see what happens if we vary the coefficients of x as opposed to the coefficient of x squared. And to do this, I'm going to construct a table. So we'll have our x value at the top, and the 3 functions I'm going to look at are x squared plus x squared plus 4x, and x squared plus 6x. And for my x values, I'm going to choose values of -5, -4, -3, -2, -1, 0. I'm going to go all the way up to a value of 2. Now, for each of these functions, I'm not necessarily going to work out the f of x value for every single value of x. I'm just going to focus around the turning point of the quadratic, which is where the quadratic dips. So just draw some lines in on my table. And some horizontal lines as well. And now we can fill this in. So for our f of x equals x squared plus x, I'm just going to focus on minus 2 to plus 2. So when I put x equals minus 2 in here, we get minus 2 squared, which is 4, take away 2, which gives me 2. When we put x is minus 1 in, we get minus 1 squared, which is 1, take away 1, which gives us 0. When we put x is 0 in here, we've just got 0 plus 0, which is 0. And I put x is 1 in here, we've got 1 plus 1, which gives me 2. And finally, when I put x is 2 in here, with 2 squared, which is 4, plus 2, which gives me 6. And in fact, just for symmetry, we could put x is minus 3 in here as well, which gives us minus 3 squared, 9, plus minus 3, sorry, which gives us 6. Okay, for my next function, x squared plus 4x, I'm going to look at values from minus 4 up to 0. So if I put minus 4 in here, we get 16, take away 16, which gives me 0. If I put minus 3 in here, we get 9, take away 12, which gives us minus 3. If I put minus 2 in here, we get 4, take away 8, which is minus 4. If I put minus 1 in here, we get 1, take away 4, which is minus 3. And if I put 0 in here, 0 plus 0, which just gives me 0. And lastly, I'm going to look at f of x equals x squared plus 6x. And I'm going to take this from minus 5 all the way up to minus 1. So we put minus 5 in first of all. Minus 5 squared is 25. Take away 30 gives us minus 5. Put minus 4 in here. We've got 16. Take away 24, which gives us minus 8. Put x is minus 3 in here. We get 9. Take away 18, which is minus 9. Put x is minus 2 in. We get minus 2 squared, which is 4. Take away 12, which is minus 8. And when we put minus 1 in, we get 1, take away 6, which is minus 5. And you can actually see the symmetry in each row here to show that we've actually focused around that turning point we talked about. So let's draw the graph of these functions. So on a vertical scale, we'll need f of x, and that's going to take us from our lowest value is minus 9 up to minus 6. So if we do minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and we can just about squeeze 6 in at the top. And along our horizontal axis, we've gone from minus 5 to 2. So we'll just use 1, 2, minus 1, minus 2, minus 3, minus 4, and minus 5. So first of all, let's look at our function f of x equals x squared plus x. We've got minus 3 and 6, which is up here. We've got minus 2 and 2, which is here. Minus 1 and 0. We've got 0 and 0. 1 and 2. And 2 and 6. And you can see clearly that this is a parabola, which, as we expected, we can draw a smooth curve through those points. So this is f of x equals x squared plus x. Next, we're going to look at the function f of x equals x squared plus 4x. And the points we had were minus 4 and 0, minus 3 and minus 3, minus 2 and minus 4, minus 1 and minus 3, and 0 and 0, which is already drawn. And once again, you can see this is a smooth curve, is a parabola, as we expected. And this is f of x equals x squared plus 4x. And the final function we're going to look at, f of x equals x squared plus 6x. And so we've got minus 5 and minus 5. So over here, minus 4 and minus 8, which is down here, minus 3 and minus 9, minus 2 and minus 8, and minus 1 and minus 5. And once again, you can see a smooth curve in the parabola shape. And this is f of x equals x squared plus 6x. So we can see that as the coefficient of x increases from here to 1 to 4 to 6, the curve, the parabola, is actually moving down and to the left. But what would happen if the coefficient of x was negative? Well, let's have a look. And we'll do this in the same way as we've just done the previous examples. And we'll look at a table, and this time we'll look at how negative values of our coefficients of x affect the graph. So we'll look at x squared minus x squared minus 4x, and the graph of f of x equals x squared minus 6x. Now, as before, we'll put a number of values in for x, but we won't use all of them. We'll only use the ones which are near to the turning point of the quadratic. But the values we'll put in, the range will be from minus 2 all the way up to 5. 4 and 5. I'll just put in the lines for our table. Okay, so for the first one, f of x equals x squared minus x, we'll look at what happens when we substitute in x is minus 2. So minus 2 squared is 4, take away minus 2 is the same as a plus 2, which gives us 6. When x is minus 1 squared is 1, take away minus 1 is the same as a plus 1, which just gives us 2. 0 is just 0 take away 0, 0. When we put 1 in, we've got 1 take away 1, which is 0. And 2 gives us 2 squared 4, take away 2, which gives us 2. And again, for symmetry, we'll do x is 3. So 3 squared is 9, take away 3 is 6. So our second function, f of x equals x squared minus 4x, we're going to look at going from 0 up to 5. When we put 0 in, we just get 0 take away 0, which is 0. When we put x is 1, we get 1 take away 4, which is minus 3. When we put x is 2, 2 squared is 4, take away 8, which gives us minus 4. When x is 3, that gives us 3 squared, which is 9, take away 12, which gives us minus 3. And you can see the symmetry starting to form here now. And x is 4 gives us 4 squared, 16, take away 16, which as we expected is a 0. And for our final function, f of x equals x squared minus 6x, we're going to look at coming from x is 1 all the way up to x equals 5. So x equals 1 gives us 1 take away 6, which gives us minus 5. X equals 2 gives us 2 squared is 4, take away 12, which gives us minus 8. When we put x is 3 in, 3 squared is 9. Take away 18, which gives us minus 9. X is 4, gives us 4 squared. Take away 24, which 16 take away 24, which is minus 8. And when we put x is 5 in, we get 25, take away 30, which is minus 5. And once again, symmetry as expected. So, as with our previous examples, we want to draw the graphs of these functions so we can see what's going on as our value, or the coefficient of x, is changing. So if we've got f of x on our vertical axis, this time we're going from, our lowest value is minus 9, our highest value is 6. So we're coming from minus 9, minus 8, minus 7, 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and we just squeeze in 6. And our horizontal axis, we've got 1, 2, 3, 4, and 5. That's obviously our x-axis. And we go right down to minus 2. So minus 1, minus 2. So first of all, let's look at the graph f of x equals x squared minus x. So minus 2 and 6 was our first point. So minus 2 and 6, which is here. Then we've got minus 1 and 2, which is here. We've got the origin, 0, 0. And we've got 1, 0. We've got 2, 2. And 3, 6. And as we expected, you can see we can join the points up here to make a smooth curve, which will be a parabola. So this is f of x equals x squared minus x. Our second function was f of x equals x squared minus 4x. So our first point was 0, 0, which we've got. 1 and negative 3, which is here. We've got 2 and minus 4, which is here. 3 and negative 3, which is here. And 4 and 0, which is here. And straight away we can see a smooth curve, which is a parabola, coming through those points. And we can label that, this is f of x equals x squared minus 4x. Last function to look at is the function f of x equals x squared minus 6x. So our first point was 1 and minus 5, which is here. We've got 2 and negative 8, here. 3 and minus 9, 4 and minus 8, and 5 and minus 5, which is here. And once again, we can just draw a smooth curve through these points to give us the parabola we wanted. And this is f of x equals x squared minus 6x. So what's happening as the coefficient of x is getting bigger in absolute terms? So for instance, we've gone from minus 1 to minus 4 to minus 6. And we can see straight away that the actual graph, this parabola, is moving down and to the right as the coefficient of x gets bigger in absolute terms. And that's when the coefficient of x is negative. OK, so we know what happens when we vary the coefficient of x squared. And we know what happens when we vary the coefficient of x. And that's both of them for quadratics. But what happens when we vary the constant at the end of a quadratic? Well, likewise, a table of values is a good way to see what's going on. So this time, I'm going to use x again. I'm going to go from minus 2 all the way up to plus 2. So minus 2, minus 1, 0, 1, and 2. And for my functions, I'm going to use x squared plus x squared plus x plus 1, x squared plus x plus 5, and x squared plus x minus 4. Now this table is particularly easy for us to work out compared with the other ones because we have a slight advantage in that we have a head start, because we already know the values for x squared plus x that go here. And we can just take them directly from our other table. And you'll remember that they actually gave us the values 2, 0, 0, 2, and 6. And in fact, we can use this line in our table to help us with all of the other lines. The second line here, which is x squared plus x plus 1, is only 1 bigger than every value in the table before. So all we need to do is just add 1 onto every value from the line before. So this would be a 3, 1, a 1, a 3, and a 7. Likewise, for this line, when we've got x squared plus x plus 5, all of this line is just 5 bigger than our first line. And so we can just 7, 5, 5, 7, and 11. And likewise, our last line is minus 4 on the end, with exactly the same thing beforehand. So it's just take away 4 from every value from our first line, which gives us minus 2, minus 4, minus 4, minus 2, and 2. So let's put this information on a graph now so we can actually see what's happening as we vary the constants at the end of this quadratic. So we've put f of x on our vertical scale. See that we need to go from minus 4 all the way up to 11. So we start at minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can just about squeeze our 11 in. And along our horizontal axis, we're going from minus 2 to plus 2. So minus 1, minus 2, plus 1, and plus 2. So our first graph is the graph of the function f of x equals x squared plus x. So that's minus 2 and 2, which is a point here, minus 1 and 0. So our first graph is the graph of the function f of x equals x squared plus x. So that's minus 2 and 2, which is a point here, minus 1 and 0. We've got the origin next, 0, 0. We've got the point 1, 2. And we've got the point 2, 6. For our next graph, actually, sorry, no, we should draw a smooth curve through this one first and label that as f of x equals x squared plus x. For our next graph, which is f of x equals x squared plus x plus 1, we need to plot the following points, minus 2 and 3. So minus 1 and 1. And you can see straight away that all of these points are just one above what we had before. 0 and 1. 1 and 3, 2 and 7. So you can imagine that our next parabola that we draw through these points is exactly the same but one above our previous one. And that's f of x equals x squared plus x plus 1. So what about f of x equals x squared plus x plus 5? Well, let's have a look. Minus 2 and 7 gives us a point up here. Minus 1 and 5. 0 and 5. 1 and 7. And 2 and 11. So if we draw a smooth curve through these points, see that gives us a parabola, and this is f of x equals x squared plus x plus 5. So finally, we'll look at the function f of x equals x squared plus x minus 4. So we've got minus 2 and minus 2, minus 1 and minus 4, 0 and minus 4, 1 and minus 2, 2 and 2. And once again, we can draw a smooth curve through these points. And this is f of x equals x squared plus x minus 4. So we can see that what's actually happening here is from our original graph of f of x equals x squared plus x, and if you like, you could have put a plus 0 there. And when we added 1, it's moved 1 up. When we added 5, it's moved 5 up. And when we took away 4, it moved 4 down. So it's quite clear to see the effect that the constant has on our parabola. When looking at the graph of a function, a turning point is the point on the curve where the gradient changes from negative to positive or from positive to negative. And when we're thinking about polynomials, a polynomial of degree n has at most n minus 1 turning points. So, for example, a quadratic of degree 2 can only have 1 turning point. And if we draw just a sketch of a quadratic, you can see this point here would be its 1 turning point. When we think about cubics, obviously cubic is a polynomial of degree 3, so that can have at most 2 turning points, which is why the general shape of a cubic looks something like this. We can see the 2 turning points are here and here. But as I said, it can have at most 2. There's no reason it has to have 2. And a good example is this, of this is if you look at f of x equals x cubed. And in fact, that would look, if I do a sketch over here, so f of x and x, that would come from the bottom left through 0 and then come up here like this. And that's f of x equals x cubed. And so we can see that the function f of x equals x cubed does not have a turning point. Another example, if we were looking at a quartic curve, i.e. a polynomial of degree 4, we know it can have up to at most 3 turning points, which is why the general shape of a quartic tends to be something like this, where the 3 turning points are here, here, and here. Now let's suppose I had the function f of x equals x minus a multiplied by x minus b. Now to find the roots of this function, I want to know the value of x when f of x equals 0. So when f of x equals 0, we have 0 equals x minus a multiplied by x minus b. So either x minus a equals 0 or x minus b equals 0. So the roots must be x equals a or x equals b. Now we can use the converse of this and say that if we know the roots are a and b, then the function must be f of x equals x minus a times by x minus b, or a multiple of that. And that multiple could be a constant, or it could be, in fact, any polynomial we choose. So, for example, if we knew that the roots were 3 and negative 2, we would say that f of x would be x minus 3 multiplied by x plus 2, or a multiple. So that multiple could be 3, could be 5, or it could be any polynomial. Okay, another example, if my roots were 1, 2, 3 and 4, then my function would have to be f of x equals x minus 1, x minus 2, x minus 3 times by x minus 4. Or it could be a multiple of that. And as I keep saying, that multiple could be any polynomial. Right, so lastly, I'd like to think about the function f of x equals x minus 2 all squared. Now, if we try to find the roots of this function, i.e. when f of x equals 0, look what happens. We get 0 equals, and I'll just rewrite this side as x minus 2 times by x minus 2, which means either x minus 2 must be 0, or x minus 2 equals 0. The same thing. So x equals 2, or x equals 2. So there are two solutions and two roots at the value x equals 2. That's what we call a repeated root. Okay, another example. Let's suppose we have f of x equals x minus 2 cubed multiplied by x plus 4 to the power 4. Now, as before, we want to find out what the value of x has to be to make f of x equal to 0. And we can see that if we put x equals 2 in here, we will actually get a 0 in this bracket. So x equals 2 is one root, and actually there are 3 of those because it's cubed. So this has a repeated root, but 3 of them. So 3 repeated roots. So there's 3 roots for x equals 2. But also we can see that if x is minus 4, then this bracket will be equal to 0. So x equals minus 4 is a second root, and there are 4 of them there, so there are 4 repeated roots there. Now, what we say is that if a root has an odd number of repeated roots, for instance, this one has got 3 roots, then it has an odd multiplicity. And if a root, for instance, x equals minus 4, has an even number of roots, then it has an even multiplicity. Why are we interested in multiplicity at all? Well, for this reason. If the multiplicity is odd, then that means the graph actually crosses the x-axis at the root. If the multiplicity is even, then it means that the graph just touches the x-axis. And this is a very useful tool when sketching functions. For example, if we had f of x equals x minus 3 squared multiplied by x plus 1 to the power 5 multiplied by x minus 2 cubed times by x plus 2 to the power 4. Now, at first sight, this might look very complicated, but in fact, we can identify the 4 roots straight away. The first one, x equals 3, will make this bracket equal to 0. So that's our first root, x equals 3. And we can see straight away there are 2 repeated roots there, which means that this has an even multiplicity. It's an even multiplicity. Our second root here is going to be x equals minus 1, because that will make this bracket equal to 0. So x equals minus 1. And there are actually 5 of those repeated roots, because the power of the bracket is 5, which means that this is an odd multiplicity. We look at the next one. X is 2 will give us a 0 in this bracket, so x equals 2 is a root there. And there are 3 of them, which means it is an odd multiplicity. And finally, our last bracket, x plus 2 here, if we put x equals minus 2 in there, that will give us a 0 in this bracket. And there are 4 of those repeated roots, which means it is an even multiplicity. So as I said before, we can use this to help us plot a graph, or to help us sketch the graph. So for instance, an even multiplicity here would mean that at the root x equals 3, this curve would just touch the axis. At the root x equals -1, it would cross the axis. And at the root for x equals 2, there's an odd multiplicity, so it will cross the axis. And at the root for x equals -2, there's an even multiplicity, so it would just touch the axis. So let's have a look at a function where we can actually sketch this now. So if we look at the function f of x equals x minus 2 all squared multiplied by x plus 1. We can identify the 2 roots immediately. X equals 2 will make this bracket 0. And we can see that this has an even multiplicity. So even multiplicity. And x equals -1 would make this bracket 0. So this would be an odd multiplicity, because the power of this bracket is actually a 1. Now, we talked before about the general shape of a cubic, which we knew would look something like this. So how can we combine this information and this information to help us sketch the graph of this function? Well, let's first of all draw our axes. We've got our f of x here, going vertically, x going horizontally. Now, we know the 2 roots. One's at x equals 2, the other at x equals -1. Now, what about the multiplicity? This tells us that the even multiplicity is at x equals 2. So that means it just touches the curve at x equals 2, but it crosses the curve at x equals -1. And I should add here that because we've got a positive value for our coefficients of x cubed, if we multiplied this out, we're definitely going to get a curve of this shape. So we can see it's going to cross through -1. It's going to come down, and it's just going to touch the axis at -2. So this is a sketch of the curve f of x equals x minus 2 all squared multiplied by x plus 1. We do not know precisely where this point is, but we do know that it lies somewhere in this region.